When I do stuff for the class, a little bit old-fashioned, I like to develop things on the board slowly. I want to show you some springs. Here are some springs. I'll pass them around in a little bit, but I want to talk about them a little bit first and write some definitions. Helical compression springs are just used in compression. They don't have any hooks for holding them. Springs are made out of round wire. The round wire can be pretty big like this one or pretty small. And here's one in my pocket, really small spring. They're like that. They have, well, this particular spring is failed. I don't want to chase them around the floor. This one has failed. This is kind of a multi-purpose spring. I had this spring almost broken, and I took it to a class to show them, and the students were kind enough to finish the job of failing it. So it's completely failed now. But a couple nice things about it. When I teach dynamics, it's a pendulum. And then when I teach springs, it's a spring. And then I talk fatigue sometimes, then it's fatigue. And in the course of taking this around, if I can get it out, one of the students was nice enough to generate this for me. And, well, I don't know if I can get it. It's a hangman noose. So one of my students was kind enough to give me a hangman noose and for my spring, I suppose, but not for me. I don't know. Anyway, that's my multi-purpose spring. I'll pass that around. Now, in a bit. The spring has 4 components that you need to know. The one is the stress. It has to have stress. One is deflection. One is material. And the other one is buckling. Might say that when I do this design for my class, what they usually do is pick a critical area and design to that critical area. And then if that one works, they check all the others, and if they all work, it works. And that's not optimization. That's just the most critical area, I guess you'd call that, is what I call that. And you want to do optimization. So everybody has a sheet. Let me talk about stress. Stress is one of the set of equations which you'll need. Now, I suppose most of you haven't taken a mechanics course yet, so you're not familiar with this, but when you push on a compression spring, it stresses mainly by a mechanism called torsion. Torsion is a twist. So these little coils are twisted. And start out with some definition. The spring is made up like this. One is little d, is called wire diameter. The wire diameter is the diameter of these little wires, anywhere from less than a millimeter to maybe 5 or 6 millimeters. And then there's a big D called coil diameter. The coil diameter is the diameter from the middle of one wire across the middle of the coil to the other wire. So those are 2 size things. And then the spring has a force which is pushed right down in the middle. From a mechanics point of view, it's assumed to be down the middle, and it has a deflection. So that's that part. And then in the torque, the torsional stress, we use Greek letter tau. You're probably familiar with Greek letters here. And you don't have to memorize any of these at all. So all of these you have defined except for the Ks, which is a constant, and it's this. And the C is called spring index, big D over little d. So you can see that. Now the spring index is said best between 4 and 12. Now, of course, it has to be greater than 1 because it's the coil diameter divided by the wire diameter. If it were too small, you wouldn't have any space in the middle. So it has to be less than 1. Those are the stress equations. And you're going to have to satisfy stress equations. Now the deflection equations, when you push on this, it goes down, of course. That's no mystery. And the y is the deflection is this, 8FD NA over dq fourth G. Couple new things. NA is called active coils. And G is shear modulus. For us, we're going to use 80.8 GPa. You just need to know those units, which is 80.8 times 10 to the 9th newtons per meter squared. You probably don't know pascals yet, but you should know newtons. Newtons is a force in SI units, and meter, of course, is a length in SI units. Now, active coils, just a word about that. N is the total number of coils. Write this up here. The total number of coils make up what is the whole length of the spring, but they don't all act in the deflection. And when I pass these around, you might get to see this little job. When they're wound real close to each other at the top, they don't participate in the deflection. And only the ones that are kind of free and open participate in the deflection. So some of the springs have a lot of top stuff like this, others just a little bit. And in the case I've chosen, you have to choose this. The case I've chosen, it's N-1. It's called plain ground ends. Plain ground ends has about a half of a coil at each end that doesn't participate in there. So that's where that comes from. Now, the other important thing is material. The strength depends on the little d, the diameter. How they make these things is called cold drawn wire. They take steel wire, and these are always steel. They take the steel wire, draw it out. The more they draw it, the stronger it gets. So the real fat springs, like that one I have on the rope, is lower strength than the real small ones, like this. So the smaller and smaller they draw it, the stronger it gets. So that's kind of a moving target, and there's several moving targets. This has a lot of equations that take a little bit of manipulation to get them to work. That's ultimate tensile strength of the steel. If you've taken material science or anything like that, you'll learn about ultimate tensile strength. Now, we don't deal with ultimate tensile strength, which is a normal stress with sigma. Sigma stands for normal stress for us, tau for shear stress. So we need to convert the ultimate tensile strength to an acceptable shear strength. And these are the equations that the spring people have come up with. This is the yield strength and shear. So that's kind of a key that you'll be working on, the yield strength and shear. And to design, usually you design with a safety factor. And we don't have a good symbol for that, so I just call that SF, safety factor. That's the yield over the design stress. And in this case, it's supposed to be 2. So it's important you get that straight. Some of the students get that mixed up, and then they have the design stress being twice the failure stress. That's not good. That's why the airplanes fall out of the sky and stuff like that. People get confused. You want the design stress to be less than the failure stress. The failure stress for you is the yield strength in shear, which depends on ultimate tensile strength, which depends on how big the diameter is or how far it's drawn out. And then the last thing is the buckling. And for buckling, you need this criterion that you want. I think I had it on here. If I don't, yeah, LF over D. That's a mistake on here. Note that it's about 8 lines down. LF over D is 4. Scratch that out if you have 4, which is the keyboard's fault. Put the wrong number in for me. Anyway, that's to avoid buckling. Has to be less than or equal to that. Now, the LF is called free length. That's how high the thing stands, free length, when you're just looking at the spring. And let me start passing some of these around now. I think I'm finished with these. You can look at them all if you want. And this wonder also. That's the free length. Now the free length, I can get that.
I'm sorry.
It's okay, they get to be jumpy sometimes.
Especially when people try to cross them.
The free length is this. The shut length plus the deflection. And the shut length is the wire diameter times the total number of coils. So I think those are most of the equations.